Good morning students, I am Dr. Ashima Saikia, Assistant Professor in Department of Geology, and I will be today dealing with the phenomenon of interference. Here you can see in the diagram that we have a crystal which is placed in the path of a ray. This is an anisotropic crystal and it has different electronic environments in its x, y and z directions. When an unpolarized ray of light which is vibrating in all possible directions enter an anisotropic mineral, it gets split into two rays which are vibrating perpendicular to each other. One is a ordinary, one we call as a ordinary ray, the other ray is called an extraordinary ray. Either of these rays can be lagging behind one another, which results in interference of colors when we observe them exiting the mineral and passing through the upper polarizer. We also have to notice that in a crystal, apart from these directions where the ray splits into two directions, we also have a direction where the ray does not split into two rays. If we have one such direction in an anisotropic crystal, we call that mineral as uniaxial crystal, and if we have two such directions in which a ray of light is not split into two, then we call those type of crystals as biaxial crystals which have two optic axes. These directions where the light ray does not split into two, we call those directions as optic axis. As we have already discussed that interference colors are the colors which we observe when the polarizers are crossed and a mineral is placed in between and the light ray is allowed to pass through it, which splits into two rays. In the case of monochromatic illumination, plain polarized light upon entering an anisotropic mineral splits into two rays, fast ray and slow ray, which vibrate at right angles to each other. Retardation develops due to differences in velocity of the slow ray, which is lagging behind a fast ray, and the distance represented by this lagging after both rays have exited the crystal is called as retardation, which is denoted by Greek symbol delta. The magnitude of the retardation depends on the thickness of the mineral and also on the differences in the velocity of the fast ray and the slow ray. So, considering this, we have the time taken by a slow ray to pass through an anisotropic mineral is Ts equal to d by Vs, that is the thickness of Ts is the time taken by the slow ray to travel, which is equal to the thickness of the mineral divided by the velocity of the slow ray. During this same interval of time, fast ray has already exited the mineral and has travelled an additional distance which is equal to the retardation. That means that the time taken by the slow ray will be equal to d, that is the thickness of the mineral divided by the velocity of the fast ray, plus the retardation divided by the velocity of the light which is travelling through that anisotropic crystal. When we substitute this, we find that delta is nothing but the distance or the thickness of the mineral multiplied by the velocity of the ray of light divided by the velocity of the slow ray minus the velocity of the light divided by the velocity of the fast ray. We know that the velocity of the ray divided by the velocity of the fast ray will be nothing but the refractive index of the mineral. As such, delta is nothing but is equal to the thickness of the mineral minus the refractive index of the fast ray or the fast ray minus the velocity of the slow ray. The relationship, that is the difference of refractive index of the slow ray minus the fast ray, is called as birefringence, which presents the difference of the indices of refraction of the slow and the fast ray. The minerals in anisotropic minerals in which, as I have mentioned earlier, in which the light does not split into two rays, that is the optic axis, we will have 0 birefringence. Otherwise, Other directions will show maximum birefringence, but most of the directions will show an intermediate value, and the birefringence is a characteristic, maximum birefringence is characteristic for each mineral, and that can vary depending upon the wavelength of the incident light which is passing through the crystal. Here you can see a diagram showing the development of retardation in anisotropic minerals. Here we can see a ray of light entering an anisotropic mineral, which on entering the mineral gets split into two rays. In the plane polarized light, we have one the slow ray and the other one the fast ray, which are at right angles to each other. When these two waves, which are split into two, emerges out of the mineral, we can see that one ray has traveled farther than the other ray, which we can see here. This difference in traveling is what is called as the retardation, which is, as we have defined earlier, is nothing but is dependent on the thickness of the mineral multiplied by the differences in refractive indices of the ray which has travelled faster from the one which has travelled slower. This results in the phenomenon of interference. When these rays will exit further from the upper polarizer of your microscope, if they interfere constructively or destructively, depending on that, we will see variety of interference color or darkness in the mineral which we are observing. There can be two situations we have. First one is when the light passing through the lower polar, it will first get polarized and then it will encounter the sample, in which it will get split into fast and slow ray. If the retardation of the slow ray, that is the lagging behind of the slow ray, is one whole wavelength, the two emerging waves are in phase. When this light reaches the upper polar, a component of each ray is resolved into vibration direction of the upper polar. As the two rays are in phase and at right angles to each other, the resolved components are in opposite directions and destructively interfere, resulting in cancellation of each other. For this, we will see no light passing through the upper polar, and the mineral grain which we are observing will appear black. But in the second case, if the retardation of the slow ray behind the fast ray is equal to half a wavelength, the two rays are out of phase and can be resolved into vibration direction of the upper polar. Both components are in the same direction, so the light constructively interferes and passes the upper polar, and which is why we see interference color. If a mineral sample is wedge shaped, as in the diagram you can see, here you have tapered end which is getting thicker on the other side, we will see that when this sort of a mineral is placed under the crossed polarizer, there will be a difference of retardation. At the thin end of it, we will have zero retardation, and it will get maximum when the thickness is maximum. When placed between cross polarizers, the area along the wedge, where retardation is a function of I lambda, that is 1 lambda, 2 lambda, 3 lambda, 4 lambda and 5 lambda, we will have areas which are dark, and areas where waves have a retardation other than 1 lambda, 2 lambda or 3 lambda, we will have the brightest illuminations. Usually the case is that if we have a retardation of I plus half lambda, we will get maximum or brightest illumination for a mineral which we are observing under cross polarized light for interference color. So far we have discussed about monochromatic illumination. So now we will discuss polychromatic illumination. Polychromatic light consists of a variety of wavelengths with the corresponding retardation same for all wavelengths. If two rays for same wavelength reach the upper polar in phase and are cancelled, the two rays for other wavelengths reach the upper polar out of phase and are transmitted from when they are exits from the upper polarizer. The combination of wavelengths that passes the upper polarizer produces the interference color in this case. Accessory plates can also be used in some cases to determine the order of interference color. Apart from this, we can also have anomalous interference color. Some minerals display interference color that are not shown in a interference color chart. This is because the dispersion of refractive indices for the fast and slow rays in this case is substantially different. This results in different retardation for short wavelength light and for the long wavelength light. As such, a different complement of wavelengths reaches the eye that if the retardation were uniform for all wavelengths and the eye therefore perceives the color differently. Now we move on to the use of the interference color chart, which is also in common terms known as the Michael Levy chart. On examining the quartz waves as we had done earlier, we saw that when polychromatic light is allowed to pass through an isotropic mineral under cross polars, we will arrive at a variety of interference as has been documented in the Michael Levy chart. At the thin edge of the wedge, the thickness and retardation are all 0. All of the wavelengths are retarded and are cancelled at the upper polarizer, resulting in a black color, that is, they are in phase. With increasing thickness and increasing retardation, the interference color changes from black to gray, gray to white, white to yellow, and yellow to red, and then a repeating sequence is followed as can be seen in this chart. The interference color produced, we have to keep in mind, is dependent on the wavelengths of light which pass the upper polar and the wavelengths which are cancelled. The primary function of the interference color chart is to allow rapid determination of retardation between the slow and the fast rays. Retardation is determined by directly observing the interference color produced by a mineral grain in thin section and by finding the same color on the Michael Levy chart. So far we have discussed the monochromatic illumination. We will now discuss about the polychromatic illumination. Polychromatic light consists of light of a variety of wavelengths with the corresponding retardation same for all wavelengths. If two rays for some wavelengths reach the upper polar in phase and are cancelled, the two other rays for other wavelengths reach the upper polar out of phase and are transmitted. The combination of wavelengths that passes the upper polarizer produces interference color. As can be seen here in the diagram, we have a ray of light which is passing through the lower polarizer, and as such it is getting plane polarized. Here we have the anisotropic mineral sample wherein the light is getting split into two rays. We have the fast ray and we have the slow ray. The retardation of the slow ray or the fast ray, if the difference between the lagging is equal to that of lambda, that is 1 unit wavelength, it will, on passing through the upper polarizer, will be in opposite directions, and so they will get cancelled. No light will pass and the mineral will appear dark. If in the case as in here, where the light is entering the lower polarizer, as such it is getting plane polarized, then we have the anisotropic mineral sample where the light is getting split into two rays, that is a fast ray and a slow ray. In this case, the retardation is 1/2 of the wavelength. Vector components of the two waves gets resolved into the vibration direction of the upper polarizer and are in the same direction, so they constructively interfere. Light passes the upper polarizer and the mineral appears bright to us with a variety of colors, which we call as the interference color. Accessory plates also are used sometimes to determine the order of interference color. Now we will discuss the use of interference color chart. On examining the quartz wedge, which we have already discussed earlier, that when we watch a quartz wedge or observe a quartz wedge between crossed polars in polychromatic light, it produces a range of colors, and this color chart is referred to as the Michael Levy chart. At the thin edge of the wedge, as you can see in this diagram, the thickness and retardation are equivalent to 0, and all of the wavelengths of light are cancelled at the upper polarizer, resulting in black color, as you can see here. With increasing thickness, that is with increasing retardation, the interference color changes from dark black to gray to white to yellow to red, and then a repeating sequence of colors from blue to green, green to yellow, yellow to red is produced, as you can observe here in the Michael Levy chart. The color gets more paler and washed out with each repetition, from first order color to the second order color to the third, fourth and fifth onwards. The interference color produced, or as can be seen in the Michael Levy chart, is dependent also on the wavelengths of light which pass the upper polar and the wavelengths which are getting cancelled, as we have discussed in the previous diagram. The primary function of interference color is to allow rapid determination of retardation between the slow and the fast rays. Retardation is determined by directly observing the interference color produced by a mineral grain in thin section and by finding the same color on the Michael Levy chart. Distinguishing among similar colors in the different orders may pose some difficulty in the first instance for students. The most direct way of determining whether a yellow interference color, for example, is a first order, second order or third order, is to carefully observe the thin edge of the grain displaying the color. Because the grain comes to 0 thickness at the edge, retardation also must be equal to 0. It is therefore possible to count the interference color inward from the edge of a grain to determine which order of interference color is displayed in the middle, which will be the true interference color of a mineral. Knowledge of retardation can also be used to determine the thickness of a thin section if a mineral with known birefringence is present, or we can determine the birefringence of a mineral if we are studying an unknown mineral of a unknown thickness. For determining thickness, we first scan the slide to find grains of quartz that display the highest interference color, meaning the color farthest to the right on the interference color chart. Only these grains are oriented to display the known birefringence of 0.009 birefringence. And then identifying the highest interference color displayed by the quartz and find it on the color chart. For this we will, as you can see here in this case, we have a color chart where on the x-axis we have the birefringence. These vertical lines are for retardation, and here we have the thickness of a mineral thin section, which is marked in nanometers or in millimeters. Here, for instance, we have a mineral of known birefringence which has a birefringence of 0.009, we will go across the radial line and join it to the lower bottom, and we will see that for a birefringence of 270 mm we have a mineral with a known thickness of 0.03 millimeter. Likewise, if we know in the lower case of this diagram, as you can see here, if we know the thickness of the mineral, which happens to be 0.03 millimeter, we can come along the vertical horizontal line and we can go down below to find out the retardation, which is about 750 nanometers, and the radial line coming out of the chart will give us the birefringence of the mineral which we are determining. We have earlier discussed about the wedge showing different set of interference color which has resulted in calculation of the Michael Levy chart. Here also you can see a wedge of a mineral grain. Here marked on it is the thickness of the mineral, and for each retardation, which is 1 lambda, 2 lambda, 3 lambda, 4 lambda, we will have dark zones, and in between we will have different orders of interference color, first order, second order, third order, fourth order, and likewise. Here also you can see a scale wherein we have here the retardations which are marked as 560 nanometer, 1120, 1680 and 2240. All these are zones of darkness, that is where we are seeing no color passing out of the upper polarizer because of them getting constructively interfered and resulting in no colors. Here we have first order color, interference color. In between, when there is a lagging of the two rays of with a fraction of half lambda, 3 by 2 lambda, 5 by 2 lambda or 7 by 2 lambda, we will have regions where we will see interference color. Here is the first zone where we have the black, which will ensue the first order interference color. Then we will have retardation at 550 nanometer, which will ensue the origin of the second order interference color. Then we will have the 1120, then we will have 1680 and then 2240, which will lead to the third order, fourth order color in increasing sequence. Above the fourth order, we will see that is retardation greater than 2200 nanometer. The colors are washed out and becomes creamy white. As I have already mentioned, if retardation is known for a mineral, it can be used to determine the thickness of a thin section with known birefringence, or can be used to determine birefringence of an unknown mineral if thickness is known. Usually it is a practice to follow the 655 nanometer line of the path difference across to find the intersection with the corresponding thickness line, usually 25 to 30 micrometer. For this intersection, we follow the sun line downwards towards the bottom right of the Michael Levy chart to pinpoint the respective birefringence magnitude on the scale on the right. Accessory plates can also be used for determining the order of interference color. The gypsum plate is generally used for quickly distinguishing between second and higher order colors and to distinguish between first order white and a higher order white. We know that the gypsum plate either adds or subtracts retardation equal to one order of interference color, that is 550 nanometer, as was discussed earlier in the diagram. As the microscope stage is rotated with the gypsum plate inserted, the retardation and interference color alternates between addition and subtraction, as the slow ray of the mineral is first parallel to the slow ray of the accessory plate and then parallel to the fast ray 90-degree later. When the mineral vibration directions are north-south and east-west, the mineral displays the magenta interference color of the gypsum plate because only one ray comes through the mineral in these orientations. A mineral displaying first order interference colors between cross polarizers will, with insertion of the gypsum plate, alternately display second and first order colors, as retardations will subtract and add as the stage is rotated. A mineral with second order colors with insertion of gypsum plate will also alternately display between first and third order colors with rotation, and this is how an accessory plate is used for ascertaining the order of interference color. In this module, we have studied about the phenomenon of interference. We have discussed that optically minerals are divided into two classes. We have isotropic minerals and anisotropic minerals. Anisotropic minerals, when observed under cross polarizer lights, we observe certain colors which are called as interference colors. How do we obtain this interference color? For this we have to study the interference phenomena. Interference phenomena is nothing but when a ray of light enters an anisotropic substance, in certain directions the ray of light gets splits into two rays. One is an ordinary ray, other is called an extraordinary ray, or it can be called as a slow or a fast ray. That means on emerging out of the upper polarizer, one of the ray will travel faster than the other one. Other than this, there are directions in an anisotropic mineral in which light will not split into two rays, and those directions are called as optic axis. In uniaxial minerals we have one optic axis, and in biaxial minerals we have two optic axes. For interference, or for us to observe interference phenomena, we have to study about retardation. What is retardation? Retardation is nothing but a multiple of the thickness of the mineral which we is observing multiplied by the difference in the refractive indices of the fast and the slow moving rays. That means on exiting out of the mineral, we will have one of the rays which is split into two rays. One of the rays will emerge earlier than the other one. As a result, there is a lagging, and that lagging is nothing but the retardation. After emerging from the mineral, when it crosses the upper polarizer, it will be at times such that the wavelength or the lagging is, if it is a multiple of lambda, then we will get the two rays will vibrate in the opposite directions at right angles. As such, they will cancel out, and we will observe dark zones in the mineral, and we will not observe any interference color, provided that the mineral, when the rays, the two split rays which are traveling with a lagging, has a wavelength difference of half lambda or multiple of it, then we will observe interference color in both monochromatic and polychromatic illumination. For assessing the order of interference color, there is a chromatic calculation which is there in the Michael Levy chart. Using that chart, we can determine the birefringence of a mineral, as well as if we do not know the thickness of the mineral, that also can be known using the Michael Levy chart. Apart from this, accessory plates also are used for ascertaining the order of interference color, like the gypsum plate, and we observe the phenomenon of interference. Interference phenomenon is also essential to understand the interference figures, which we will discuss in our next class. Thank you.